because you learned something about me.
Wasting is not a...
Yeah, we just didn't spend 10 minutes on chemistry. We talked about chemistry,
Yeah.
just chemistry that you should have known 3 years ago. So,
Well, chemistry is in like chemistry.
yeah, that's true. We did talk about chemistry. Okay, so, chapter 10, solids and liquids. Sounds simple, but we're going to get into something a little bit more. So we have been living in this area, right? We've been living in the intramolecular bonding. So intramolecular bonding is super strong. This is within compounds, right? So this is metal-nonmetal, which is ionic, right? Or two nonmetals, which is covalent. Covalent is actually stronger than ionic because covalent has those shared electrons. What we're going to be getting into this chapter is intermolecular forces. So this is bonding, ionic bonding, covalent bonding. These are forces, and they're all weak. All right? So if you're comparing these to here, these don't even hold a candle to over here. I think you'll see later, but like covalent is like a 100, and these are like a 1. All right? If you're comparing strengths, which you wouldn't compare strengths, because these are something completely different. They're intermolecular, so they're within a molecule. They're weak. They're just attractions. So be careful and don't call intermolecular forces bonds, because they're not. Okay? So let's review solids, liquids, and gases. You guys have all seen that picture before, right? Yes? Still true. All right? I just wanted to put that there to reassure you we're still talking about solid, liquid, and gases. So we have to actually understand the properties. There's different types of solids. There's a whole new world available. And we're going to talk about it. So solids can be two different ways. The first way is crystalline. So Crystall. I think that's crystalline, which is ordered. So an example of a crystalline solid would be a diamond, right? A diamond is a crystalline solid. All right? What? Salt would be a crystalline solid. But you can also have diamond in another form, which is just coal, right? So this is also carbon, not in a crystalline structure. This is in its amorphous structure. So that's amorphous, also known as not ordered. So same solid, ordered different ways, same formula, it's just ordered or arranged differently. And how do you get a diamond? Extreme what? Pressure and usually high temperature, right? But mostly from high pressure. You learned that in geology from Mr. Knight, right?
Yeah.
Anybody take geology? No. Oh. Okay. This is the main difference between, there it is, coal and diamond. Good, my train of thinking still works. So, intermolecular bonding, and I probably shouldn't have said bonding, it should probably be forces, but you guys are good with it. It's still based on blank blank. Yep, there it is. Coulomb's law. It's still based on Coulomb's law, or attractions between opposite charges. And those charges are usually weak. Charges are usually weak, resulting in intermolecular forces to be relatively small compared to intramolecular forces. This is all stuff I've already said. So, to summarize, intramolecular is bonding within a molecule. So this is bonding within a molecule. Bonding within a molecule. And there's two types. One is ionic and one is covalent. One is ionic and one is covalent. I'll move down so you guys can actually see that. Ionic is by what? What's happening in ionic? Transfer of electrons. So a transfer of electrons. And covalent is sharing, because we say that sharing is covalent. Intermolecular are more, I'll say, bonding attractions. And we'll put attractions in quotations, because they're attractions. All right? Between molecules. So this is within the molecule, and this is talking about how are molecules going to actually interact with each other. So we talked about intramurals. Now we're talking about inter, between the actual different schools or molecules. We're going to take the school example. Flip the page. So the main question that you have to ask yourself when you're dealing with this is there a permanent, anybody have a guess? Dipole moment. You got it. Is there a permanent dipole moment? Or in other words, is it what? Is it polar? You got it. Is it polar? So here are the examples of intermolecular forces with permanent dipole moments. Permanent dipole moments, and I said polar covalent. So, ionic solids. I know that this isn't an intermolecular force, but I still want to review it, okay, from last chapter, because there's going to be something about ionic on the test, about like dissolving it, and that means it can conduct electricity or has a high melting point. We still have to review this. So let's use salt, sodium chloride. Sodium chloride is very, very polar. It's very polar, and these form a crystal lattice, right? We did this last chapter. Form a crystal lattice, and then we can calculate the lattice energy, right? Like you did on the test, hopefully, and got it right. And these are very, very strong, I guess, forces. I'll say intermolecular forces. Now, I just caution saying that they are intermolecular forces because they're really intra, but sometimes you'll see it as inter. I don't really count it as inter, but sometimes you'll see it like that. Dipole-dipole is the first actual intermolecular force. So dipole-dipole, you're probably going to have what? How many dipoles? You're going to have 2 dipoles, right? It's really fun if you say it really fast. Dipole, 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 dipole. Try it. It's fun. It comes off the lips just very nice, like dipole, 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 dipole. It's really nice. Yeah, kind of. This is where electrons are not evenly distributed. So if you remember last chapter, we kind of drawing those arrows, right? And the arrow would have a positive side, and it would have a negative side, right? Yes? Yes? You guys remember this from last chapter? I mean, there's a positive and negative side, is all I'm saying. All right? These positive, negative, and a dipole-dipole, this is going to cause molecules to line up to maximize what? What is it going to want to maximize? Positive to negative attractions, and going to minimize the positive to positive or the negative repulsions. So if you look at page 385, this is in color, all right? You can see what a dipole-dipole interaction looks like. So the positives want to get by the negatives, and the negatives want to get by the positives. Is it perfect? No, it's not perfect. But you can kind of see what that looks like. So I have a non-color picture here and a color picture on there. There's other types of dipole-dipole interactions. So when a polar, this is key, when a polar molecule approaches a non-polar molecule, all right, and induces a dipole on that. Am I on the screen? No. There it is. When a polar molecule approaches a non-polar molecule and induces a dipole in it, this is called a dipole-induced dipole interaction. So imagine this, right? Imagine this. So let me just kind of draw this. I'm going to try to draw it up here. So here's something polar, right, with a positive and negative side. Here's the molecule. Cool? So definitely polar. And then here's this other molecule, which has positive, negative, just kind of all floating out there even. Yes? This is before. This is very, very rough. All right? Here's the after. This molecule is going to get closer to this molecule. So here's the after. This molecule is still polar. But as this molecule gets a little bit closer, right? What could this negative pull a little bit more towards it? Positive. You could start pulling the positives a little bit closer than the negatives. That's what I'm talking about here. That's what I'm saying for an induced dipole. So something that wasn't necessarily polar, becomes a little bit more polar, is what I'm saying. A third force involving dipoles is when a polar molecule interacts with an ion. This is called an ion dipole force, all right? It's kind of basic, all right? I'm just throwing them out there so you've heard of them. And each of these forces that all include dipoles all rely on Coulomb's law. So there has to be opposite charges in order for there to be a dipole. Because di means two different charges. Flip the page. Here it is. We had Coulomb's law. Here's the other thing. All right, like the answer that can almost answer anything. The most important special type of dipole-dipole and the strongest intermolecular force is hydrogen bonding. Have you heard of hydrogen bonding before?
Yes.
You should have. Where? Biology. All right? And I like to say that hydrogen bonding is fun. Okay? Because it's always between hydrogen, fluorine, oxygen, or nitrogen. All right? So hydrogen bonding is fun. Maybe. I don't know. However you guys remember. All right? Or some people remember HNOF. I don't care how you remember it. But when hydrogen bonds with nitrogen, oxygen, or fluorine, the positive end of hydrogen is attracted to the negative of an, let's just say, oxygen. All right? Why does this happen? Well, this is a huge difference in electronegativity, right? So the single electron, when it bonds, is only held to one side. This is so important. It's only held to one side of the nucleus. I'm talking about hydrogen. Leaving the other side completely exposed. Leaving the other side completely exposed because there's no what in hydrogen? There's no shielding.
Yeah.
Right? There's no shielding. So the other side's completely open, and this is why water has two hydrogen bonds, has such a high boiling point. All right? Because water is hydrogen bonding. These substances are also usually more viscous. A lot of times. Now, water's not super viscous, but a lot of times when you have a lot of hydrogen bonding, it's going to be thick. All right? Because it's super, super attractive. So it's going to be thick. T-H-I-C-K. Thick. Not the other one. I had a lot of sugar for lunch, guys. Okay? I had a lot of sugar for lunch. So, what would this look like? So let's draw some bent water molecules. Here's a bent water molecule. So here's a hydrogen bond connected to another oxygen, which is going to be bent. Right? And this is going to be attracted to another oxygen, which is going to be bent. Yes.
That's right.
And then maybe this hydrogen is attracted to another oxygen, which is going to be bent. Something like this. Now, they don't like this, but that's okay. They don't want to be by each other, but it's not going to be perfect. I made it decent. And notice that I didn't draw bonds. I drew like dots because these are just attractions, okay? And you can see that these are between molecules. Because water has what type of actual bonds? Covalent, right? But the attractions are hydrogen in between. So when you have a lot of water molecules, that's why you have something like the pool at Freelander, which they fill up way before you actually want to use it. Because water also has a high what? Specific heat. All because of hydrogen bonding. All right, SMAT. So we're starting to relate some earlier stuff now to our intermolecular forces. So that is our polar intermolecular forces. We also have non-polar intermolecular forces, or where electrons are equally. These are equally shared electrons with no permanent dipole moment. And I've already kind of showed you what this looks like. This is called London dispersion forces. Or sometimes I think you'll hear it called like van der Waal. All right? So either one is okay. But this is the weakest of all intermolecular forces. I'll show you the scale in a second. So once again, as one molecule, as one nonpolar molecule, right, approaches another nonpolar molecule, the same idea happens. It can cause the electrons to polarize, right? Or start to unevenly spread and create temporary holes. So flip it over to, I forgot to change the page on this one, to the new book. Page 387. Page 387 shows this. So on 387, you can see you've got two nonpolar molecules. You see those electron clouds, atom A, atom B? And as they get closer to each other, well, you start to pull the positive side of one towards the negative side of the other. Different than an induced dipole, right? Because these are not dipoles. So if you put something nonpolar with something nonpolar and they get close enough to each other, you can polarize them. You can polarize them. This is like a balloon. When you rub a balloon on your head, right? A balloon is made of rubber, right? If you put a balloon on a wall, is a wall polar? No. Is the balloon polar? No. But if you can create an overload of charge on one side of the balloon, and you put the balloon against the wall, it can pull some electrons towards it, and that's why it sticks. All right? What eventually happens to the balloon? It falls down. Why? Because the electrons redistribute. That's it. All right? Bent. Helium.
Yes.
Helium, the most reactive nonmetal. All right?
Great.
Does that make sense? I feel like I explained that pretty good.
Yeah.
Okay. So the electron cloud is key for London dispersion forces. In one molecule is going to cause the cloud in another to move. So the electron clouds are kind of moving. The larger the electron cloud, the more it can polarize another molecule, the more the London dispersion / van der Waals forces. So we'll have larger electron clouds. Larger what?
Atoms.
Larger molecules. You got it. Larger molecules. So is it possible to have a London dispersion force that's actually greater than a hydrogen bond? Depending on the size, it's possible.
It's just temporary.
It's temporary. You got it. Flip the page. We're moving pretty good. So here we go. So here's a little bit of a practical application to this. So PCl5 or SCl5, in your own head, which one has more London dispersion forces? Think about that. So once again, which one has more London dispersion forces? Which one?
PCl.
PCl5. Why?
Larger.
It's bigger, right? The nucleus is not holding on to the electrons as much, agreed? So now we're back to trends once again. We're back to trends again once again. Back to trends again once again? All right, PCl5 has more LDFs, which means it has a higher, most likely, melting point or boiling point, and it's also easier to polarize. It's easier to polarize. Okay? Now I have something else here. All right? What is CH4? Methane. And methane is a what? It's a gas. It's a hydrocarbon. Yes? Anybody have a guess of what C8H18 is? Octane. And where do you see octane? What?
Gas.
It's a gas, right? You have high octane engines. That's a liquid. Anyone know what C25H52 is?
No, not that.
It's wax.
Whoa.
That's candle wax. And candle wax is solid.
Wait, we burned that?
What?
We burned that?
Yeah. Yes.
Is it safe?
Yeah.
It just looks really big.
When you burn something, all you end up with is CO2 plus H2O, right? Combustion is always carbon dioxide plus water. So why do I go from gas to liquid to solid? Because I have larger what? These are all nonpolar, agreed? Yes? But my electron cloud is getting much, much larger. So my London dispersion forces are much, much stronger. So I can literally go from a gas to a liquid to a solid. And these are all nonpolar, all London dispersion. But because this is so huge, it's actually a solid. Because of the London dispersion forces. Chemistry is pretty cool, all right? Chemistry, I came with that on my own, thank you, all right? Chemistry is pretty cool if you actually understand what's happening. So, all nonpolar, but because the electron cloud is so big in this one, it's a solid. Okay, so the weakest to strongest intermolecular forces would be the weakest would be London dispersion. The next weakest would be dipole-dipole. just your regular dipole-dipole. And then the strongest is going to be hydrogen bonding. Now, is hydrogen bonding dipole-dipole? Yes. But it's a special form of hydrogen bonding. What's that?
This is only the bond, right?
Yes, because it's only with fluorine, oxygen, and nitrogen. So, on your own, try to rank these from lowest to highest conductivity. Which one can conduct the least to which one can conduct the best? Think about this. When we're talking about conduction, what do we have to talk about? Delocalized electrons, right? When you're talking about stuff being conductive, you have to think about those delocalized electrons. So you have to ask yourself, which one of these is going to allow electrons to flow the most easily? The weakest force, right? The one with the weakest attraction is going to allow for electrons to flow the most easily. Head nod if that makes sense.
Yeah.
So the lowest conductivity is going to be hydrogen bonding, right? Hydrogen bonding. Your middle is going to be your dipole-dipole. And then your highest is going to be your London dispersion, or van der Waal, however you want to say that. So, here we go. We got a trend here. These are group 18 elements. These are group 18 elements. And it could say, explain this trend using intermolecular forces. So take a look at these. How would you describe that? What'd you say?
I was about to say they're decreasing, but it's negative, so that would be.
Well, what's happening to the boiling point? The boiling point is getting larger. Agreed?
Yeah.
Because it's becoming less negative. Why?
Size is
Yeah.
The size is increasing, which is also increasing the electron cloud, which also increases the... Yes, that's a great answer. All right? So, the larger molecules have larger electron clouds. Thus, I don't know why I said thus. They're more polarizable and have higher LDFs. They have higher London dispersion forces. That's a pretty good answer. That would get you the point on the AP test. All right? That would get you the point on the AP test. You can't just say bigger is more London dispersion forces. Nope. That will not get it. You got to talk about the electron cloud. Got to talk about the electron cloud. So you see here, this is a very crude comparison, strengths of your covalent bonds and intermolecular forces. So it would be London dispersion would be like a 0.005, dipole-dipole 0.5, hydrogen bond is 10 times stronger than that. So we have London dispersion, what's dipole? Is that 100 times stronger?
Yeah.
Then we have 10 times stronger for an H bond. Ionic would be somewhere like in between this, all right? But a covalent bond is 20 times stronger than a hydrogen bond. So that's just a rough comparison of how strong these actually are. How are we feeling so far?
Good.
Okay, turn the page then. Let's keep going. Page 386. Are you still on that page?
Yeah.
So this is similar to what we have on page 386. So take a look at this graph. I look at page 386 actually. It's a little bit better because it's in color. My boiling point, so I'm at group 6A, right? So that's group 16. Look at the yellow line. I have H2O, then it goes down a lot to H2S, then it starts climbing back up. The same thing happens for HF. If I'm in group 7, HF, pretty high boiling point, then it goes down when I get to Cl, then it starts climbing back up. NH3, pretty high. Now I'm in group 15. Then it goes down when I get to P, starts climbing back up. But in group 14, they all go straight up. Why? in those first three groups, H2O, HF, and NH3 are all what type of bonding? Those are all hydrogen bonding. So in group 15, 16, and 17, do you guys see it now? I've got HN, HO, HF. So after that, when I go down to the next one, I no longer have hydrogen bonding. What type of forces do I now have? London dispersion or dipole-dipole, right? So that's why there's that big drop down after that first one. But on group 14, there's no hydrogen bonding for carbon, so now it's just based on what? Size. Head nod if that chart makes sense. Okay? Cool. That's that chart. Kind of cool. I could see there being a multiple choice question like that on the AP test. As long as you understand that there's hydrogen bonding in the first ones and not in the other ones, you're good. So, when the intermolecular forces of two substances are similar, the substances tend to be miscible. They tend to be miscible. In other words, they mix. M-I-S-C-I-B-L-E.
Like when you could miss it.
Right, exactly. You can mix it. It sounds like mixing. So, mixable and miscible sound just like each other, and that's actually what it means. Like, I'm probably going to give it away. Is that what I'm about to talk about? It's not, but oil and water, right? Oil would have what type of intermolecular forces? Oil is a non-polar, so that's going to have what type of forces? London dispersion forces. Water has what type of forces? Hydrogen bonding. Are those going to mix? No. That's why they sit on top of each other. Because their intermolecular forces are different. They do not want to dissolve or mix into each other. You have to have similar intermolecular forces to mix. Now, are the majority of particles or molecules going to be polar or non-polar? Most of them are what? Polar, right?
Yeah.
Most are polar, which is why water is considered the universal solvent. All right? We're starting to prove a lot of things here with intermolecular forces. So not only is water polar, right? Has a positive or negative side, right? It also has the hydrogen bonding. Hence, water is the universal solvent. Kind of cool. What?
I was like, everything's great when it was like, there's no reason, it's just this, and
When
now
it-
there is reasons.
I know. When it used to just be like dissolves like, okay? So don't say like dissolves like. So, for example, ionic substances, those with ions, charged particles, tend to be attracted to and dissolve, right? Those are going to dissolve in things that are polar, like water. This explains the like dissolves like. See, I told you I was going to get ahead of myself. I always do because I wrote this. So, only when the solute-solvent interactions are relatively strong compared to the other attractions will the solute dissolve. So it's not going to dissolve unless there are actual interactions with the intermolecular forces. We are cranking. I'm loving this. Let's keep going. So take a look. So we have pentane and butanol. Doesn't really matter why they're called that. That's just what it is. Letter A is, what is the significance of the molar masses being the boiling point. I didn't put something on here. The boiling point of pentane is 36 degrees Celsius. And the boiling point of butanol is 117 degrees Celsius. You have to know that for this to make sense. So, this should make a lot more sense now. A, what is the significance of their molar masses being approximately the same? If their molar masses are the same, what else is probably the same?
They're London.
Yes, that means that their London dispersion forces, right, should be about the same. They should be about the same. So my LDFs are pretty similar between these two molecules. Agreed? If they're the same size. But they have similar masses, but a large difference in the boiling points. Why? There it is. There's a hydrogen bond in butanol. That is a difference in 80 degrees Celsius. That one hydrogen bond. So you would say the hydrogen bond in butanol. The hydrogen bond, I spelled that wrong, in butanol is the difference. Number 2, the boiling point of HCl is negative 85. The boiling point of chlorine is negative 34. Discuss the differences boiling points of these substances in terms of intermolecular forces present. So talk with a partner and say why. All right, talk with a partner and actually why. Why is that?
And there's more.
The one is
Oh,
HCl.
The HCl is going to be much smaller.
So it's smaller. That means the LDF would be smaller.
These are both going to have what type of bonds? These are both London dispersion, right? These are both LDFs. But what?
CL2 is bigger.
CL2 is bigger. You got it. CL2 is larger. CL2 is larger. How much more do we have to go?
Is there a dipole moment in HCl?
There is a dipole moment in HCl, but it's not enough to really matter. All right? A lot of these have a lot of molecules. Here's the thing. Pretty much every molecule has London dispersion forces, okay, of some sort. So that's the thing that you really have to understand is London dispersion is in every molecule. This is probably a good point to stop because the rest of this is all kind of related. Actually, you know what? We can probably finish. Let's keep going. Forget it. We might be able to finish this. All right, let's keep going. So now we're talking about vaping. Okay? So vapor pressure is one of the properties of liquids. So I'm going to give you the book definition. So the book definition is vapor pressure is equal to the pressure exerted by a vapor in thermodynamic equilibrium with its condensed phases at a given temperature. What the heck does that mean? When is a liquid going to be in thermodynamic equilibrium?
Right before it, does either freezes or.
Yes, at the phase change, right? You're at thermodynamic equilibrium during a phase change because that's this part of the graph when the temperature's not changing, right? When the temperature's changing, it's not at thermodynamic equilibrium. If it's heating up or cooling down, not by when it's here, thermodynamic equilibrium. My definition is the pressure produced as molecules escape a liquid. So basically, how easily can molecules escape a liquid is what it comes down to. Yes?
So is water in thermodynamic equilibrium if it's just in a cup?
Nope. It'd be a thermodynamic equilibrium if it was boiling or if it was freezing. If it's just in a cup, it's probably just kind of sitting there. So the number, here's the thing. Here's the thing. You could calculate it for water in a cup, but technically thermodynamic equilibrium, the vapor pressure is based off of at the phase change. All right? So you get the vapor pressure from the phase change. You could do it for water in a cup, but it's going to be a little bit different, a little bit lower because of the lower temperature. So water in a cup is not at thermodynamic equilibrium because it's not exactly at a phase change. Water in a cup is just sitting there. It's just water. So you would ask yourself, it's not. So water in a cup, it's sitting there, but it's not at thermodynamic equilibrium. Okay? And this is also technically all under 1 ATM, right? So water in a cup here isn't even at 1 ATM because we're not at sea level. But that's...
It's just confusing because you just told me that it's at equilibrium and it changes. It doesn't it's just
Well, the temperature's not changing during a phase change, though.
uh-huh.
During a phase change, the temperature isn't changing. So I can see how you're confused because water just sitting in there in a cup, the temperature's not changing, right?
Yeah.
Can water evaporate in a cup? Yeah, it can. It can. But really, 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 really slow. So basically, how well can water evaporate from a cup? The vapor pressure of water in a cup would be higher than the vapor pressure of water that's boiling. Because think about it. It's easier for water to escape when it's at 100 than it is for water in a cup. Those are two different vapor pressures. But the vapor pressure is determined based on boiling. Is that helpful, Brendan?
Yes.
It's determined off of the boiling point or the freezing point. You can have different vapor pressures. So we're going to be determining vapor pressures at a certain elevation or a certain elevation, or at this temperature or at this temperature. Okay? Okay. So, how easily can molecules escape? So, the more molecules can escape, the higher the vapor pressure. The higher the vapor pressure. Liquids continue heating until they reach an equilibrium point called boiling point. Temperature and vapor pressure are directly related. So that's what I was talking about, Brendan, that you're going to have a different vapor pressure for the cup of water versus the water boiling. But water's official vapor pressure is determined by boiling. Are we all on the same page? Okay. The vapor pressure of a liquid is lower than the vapor pressure above it until it boils or reaches equilibrium. So, is water going to have a higher or lower vapor pressure in Colorado? Lower, right? Because there's less what pushing down on the water in Colorado? Less air pressure, right? It's literally the pressure keeping those molecules as a liquid. It takes longer to boil it. You got it. So it's kind of like opposite thinking. You'll get it as you think about it more. So if I have a liquid in a sealed container, I gotta flip the page. Oh, this one I hate that. Consider a liquid in a sealed container. Even if the liquid is below its boiling point, here's what we were talking about. A few molecules will have enough energy to overcome the intermolecular forces holding them together and escape into the vapor pressure phase above the liquid. The weaker the intermolecular forces between molecules, the easier this process is. And the more molecules will enter the vapor phase. This causes a relatively high vapor pressure. So in summary, weak intermolecular forces cause liquids to have low boiling points, and those are said to be volatile. So something is volatile, it evaporates very easily. So something like ethanol has a really low boiling point. Like your alcohols. You put those on a table, they immediately evaporate because they have super low boiling points. Also very volatile. We're going to do a lab like that next week. It's pretty cool. So in summary, we can make the forces cause liquids to have low boiling points, they're volatile, and we'll have high vapor pressures, and vice versa. This is a review of Maxwell-Boltzmann. So flip it to page, let's see if I did this right, 417. This one looks like I actually fixed it. Page 417. There it is, Maxwell-Boltzmann. So you can see that at the top of page 417, at a higher temperature, right, you have more molecules available to actually break away from the surface than at a lower temperature. This is just another version of Maxwell-Boltzmann, is what it comes down to. Higher temperature, you have more molecules, for your view, would be over here, right, than at a lower temperature. Just Maxwell-Boltzmann. So we can do like Maxwell-Boltzmann like 4 different ways now. So kind of exciting. There's calculations. And the nice thing about the calculations is they're plug and chug. All right, they're plug and chug. So the enthalpy of vaporization is equal to the energy required to vaporize 1 mole of liquid at 1 atm. So there's a couple different versions of this. So I'm going to tell you what everything is first. Delta HVAP is the heat of vaporization. That's the enthalpy of vaporization. We're going to have PVAP, I'm defining these, is your vapor pressure. PVAP is your vapor pressure. We're going to have C, which is a constant. All right? It's a constant. We're going to have R, which is now the universal gas constant, which is 8.3145 joules per mole times Kelvin. 8.3145 joules per mole Kelvin. And your temperature is going to be your temperature in Kelvin. So your Kelvin temperature.
Wait, what is that? Oh, T.
T is going to be your Kelvin temperature.
What's the HVAP again?
HVAP, that's just your heat of vaporization. So
It's
HVAP
not-
is what we're solving for.
Can you
Sorry.
slide it over?
I just wrote HVAP as your heat of vaporization. I'll zoom out a little bit. So, your equation looks like this. The natural log of your vapor pressure is equal to negative of your heat of vaporization over R times 1 over T plus, that's in parentheses, plus C. Well, scientists, all right? So, then there's another guy called Clausius Clapeyron. Clausius Clapeyron. That's his actual name, Clausius Clapeyron. Who's like, we can make this better.
Yeah,
All right?
Just like his name.
Clausius Clapeyron, yes. Another version of this is the natural log of PVAP of temperature 1 over the PVAP of temperature 2 is equal to delta HVAP over R times 1 over T2 minus 1 over T1. Which one's easier to use? I think the second one. All right?
Yeah, there's
Neither.
two
But because you have natural logs, you're going to be raising some stuff to the what? To get rid of that? To the E. Yeah. So you're going to have some E work to do in here. Not hard, just plug and chug. That's actually all of the written notes. We'll finish the rest. Well, actually, no, it's not. There's more to do. But that was a good amount for the day. Good amount for the day. Yeah, if we would have done the 10-minute story time, we would have finished.